In question 2b, we want to construct the Green's function associated with this differential equation. As usual, we write down the general solution to the corresponding homogeneous equation. In this case, it is a linear combination of hyperbolic sine and cosine functions. The Green's function is expected to be of a similar form where we let the earlier coefficients a and b to be functions of z. However, the Green's function is expected to have a discontinuity at x equals to z, so we let the coefficients to be different at x smaller than z and x greater than z. So our expression for the Green's function is split into the top and bottom lines. Our task now is to determine the forms of a, b, c, and d. This is done by requiring that the Green's function satisfies the three conditions specified in the lecture notes. Firstly, to invoke the boundary conditions. As given in the question, the function at x equals to 0 is equal to 0. This leads us to the following, where the hyperbolic cosine becomes 1 and the sine is 0. The conclusion is that here a is equal to 0. The second boundary condition is at x equals to 1, where the function is also equals to 0. Putting x equals to 1 into the Green's functions, we can express d in terms of c. Using this expression of d, we update our expression for the Green's function by substituting d into the equations. In the second line, the expression can be simplified by using an identity for hyperbolic functions. The second condition for the Green's function to satisfy is that the function must be continuous at x equals to z. That means at x equals to z, the expression at the first and second line of the Green's function must be equals to each other. So now we can express b in terms of c. Accordingly, our expression for the Green's function is updated. It is now left with one unspecified function c, which we can determine using our third and final condition. In this third condition, g jumps by 1 at x equals to z. To evaluate c, we first take the first derivative of g to obtain the following expressions. Since the derivative jumps by 1, the difference between the second and the first line of dg dx is equals to 1. An observation can be made if we factorize some common terms outside. Then the terms remaining in the square bracket can be simplified by another hyperbolic function identity. The remaining expression in the argument can be further simplified. The terms proportional to z in the argument cancels out. What is left is the hyperbolic sign of alpha, which cancels with another one appearing in the denominator. So finally, our expression for c is that c equals to a negative hyperbolic sine alpha z divided by alpha. With this result for c, substitute and obtain our final expression for the Green's function.